Okay, so we are also live on YouTube. And let me share the screen. Sure. Okay, so the topic of today is multi-agent reinforcement learning. And we'll basically be going through a survey paper that I think is very well done. And basically, I base my presentation on that. But before stepping into that, let's set up the context. So what is the problem of multi-agent reinforcement learning, how that differs from single-agent reinforcement learning, and so on and so forth. So a multi-agent reinforcement learning problem is typically formalized in something that is similar to an MDP, but it's called partially observable stochastic game or Markov game. And basically the structure is the one that you see in this figure. Was copyright is from Justin Terry, where we have an environment and we have multiple agents, each of which can execute some action in the environment. And each agent receives an observation that might be different from other agents, and also a reward that can be different from other agents. Now, whether the observation is different or is all the same, or the reward is the same or different, that generates sub-problems in multi-agent reinforcement learning that we'll be briefly discussing. Anyway, if we want to formalize this POMG, we know that this is something that has a set of states, a set of actions, each composed by the set of actions of each agent. There is the usual state transition function, the reward function. And then, in addition to that, we have the observation function, which is something that maps to the state to an observation. And each of these observation functions is private, is individual to each agent. Similarly, by means of this function, we can generate private observations for each agent belonging to the observation space. Then we have the usual gamma, the discount factor, and n, which is the number of the agents. So the problem is quite more complex compared to a standard reinforcement learning problem, a standard MDP, because we have two more things to take into account. So one example is the following. This is an environment from petting zoo, and it's called piston ball. And in this environment, basically each agent is a piston, and they are working in a collaborative task, meaning that they all want to push the ball from the right to the left. And in order to do that, they only have an observation space, which is limited. As you see from this image, they have basically a visibility of three pistons, one of which is the agent itself, and they only see that. So there is a partial observability issue here. In addition to the fact that we don't know what's happening outside to the observation space, which is exactly this partial observability problem, we also have no stationarity problem, because the actions for the agent do not always have the same effect based on the current state. Why? Because if there is, for example, if we're controlling this agent in here, and there is an agent outside the observation space of the agent itself that is up, then the ball will go back. So the action will not have the effect that we would be expecting. But let's see more in details what are these issues. So the challenges in multi-agent reinforcement learning are, of course, partial observability, which is exactly what we just said, and this is a clear example of it. Agents do not have access to the true state. They only have an observation, which is limited, and each agent receives a private, right? This is a private to this agent, private observation, which is partial compared to the state of the environment. And it only gives us the partial information with respect to the current state. So based on that, the agent chooses an action that, of course, is derived from its policy, but it's conditioned only on this private observation. The other problem is the one that I was discussing, which is the non-stationarity problem, because the environment changes and its dynamics changes according to the actions of all agents. So from the viewpoint of a single agent like this, having this exact same state, this exact same observation, and executing the exact same action will lead to completely different rewards. And so the reward itself is non-stationary. The dynamics of the environment is non-stationary. And so if you do standard reinforcement learning on top of this, you need many, many samples. You need a lot of information, because you not only account for the stochasticity of the environment, but you also account for the fact that this stochasticity is continually evolving. And so the agent has a lot of problems in learning that. And last but not least, there is a very hard problem, which is credit assignment. This is already a problem in reinforcement learning, because if you want to understand which action led to that reward, you need to take into account the fact that we're dealing with a temporal sequence, and so data depend on each other. And so we don't know exactly which action has led to a certain reward, but there are workarounds on that. In this case, you not only you don't know which action led to a certain reward, but given that the reward depends also on other agents, you don't know even which agent was responsible for the received reward. Okay, so let's say that two agents are collaborating for bringing an object into a certain location. Then, and let's say one of the agents is doing everything by itself, and the other one is doing nothing. They will still receive both the same reward, but none of them knows if it was good or not what they did, because they anyway received the positive reward, so the positive signal. And it's very hard for them to distinguish between in understanding which one has credit for that. Okay. Cool. Are there any questions regarding this? No. Okay. So let's recap a bit what we just said. If we put together these issues and we sum together, for example, the fact that we have partial observability and non-stationarity, basically we are breaking the Markov assumption, right? Because the Markov assumption says that the state is sufficient for a certain agent to take an action and to basically derive the consequences of this action. You don't need to know the history before that, and you don't need to know any other thing accept the state. Now, this is not true anymore because the state only comes in the form of an observation, which is partial, and the environment is changing its dynamics. So this marker assumption is broken. Also, as we have seen, many reinforcement learning algorithms use experience replay buffers. And if you do that, basically, due to non-stationarity, the transitions in the experience replay become quickly invalid because the environment is changing. It changes as a result of the actions of all the agents. And the transitions that we store are basically not useful anymore. Also because the other agents change as well. The issue of credit assignments leads to very high variance in the problem, which is very difficult then to solve and learn. And all in all, we get a very high sampling efficiency by summing up all these three components. So in order to do multi-agent reinforcement learning, compared to single-agent reinforcement learning, you will get, you will need many more data. Typically, the setting in which you can do multi-agent reinforcement learning can be three. One is the cooperative setting, another one is the competitive setting, and finally we have a mixed setting. So the cooperative setting is where the reward function is the same for all the agents. So this is why I was saying, depending on how we say the reward is the same, the reward is different, we get different categorizations of the problem. In collaborative problems, the reward is the same for all the agents. So they work together to optimize a certain performance of a larger system. And you can think of this like, for example, urban traffic control, air traffic control, electricity generator scheduling, but even more simply, exactly the task that I was describing before, like two agents that have to collaborate to bring an object to in a certain location. The competitive setting is that of typical games like backgammon, Go, StarCraft, or other games, where basically if an agent wins, then this implies the loss for another one. So this is a zero-sum game. If I win, you lose. And this is exactly what is described here. So one winner, one loser. In non-zero-sum games, then we are in a cooperative setting, for example, they are in a win-win situation. The mixed setting is also a non-zero-sum game, and here there are no restrictions that are imposed on the reward function, and there could be elements of both cooperation and competition. And this is, for example, the case of RoboCup, right? Where you have, if you don't know RoboCup, RoboCup is a worldwide competition where there are teams or robots that participate by playing soccer or football, which I would prefer the name. So they play football, and the goal of this is having by 2050 a team of robot players winning against humans. So far, we have standard robotic platforms that are used in order to compete between themselves in teams. So the competition part is the competition between teams, but there is also the cooperation part where each component of the team needs to collaborate in order to achieve the goal of the team, which is winning. Okay, so this is, we just discussed on a possible setting depending on how the reward is structured. So we say the reward is one component. The other component is the observation. Is it the same for agent or is it individual to each agent? Based on that, basically we have a differentiation between independent learners and joint learners. So in independent learners setup, we basically ignore all these problems that we just discussed, and we say, okay, we don't care. We treat it as a standard MDP, and we have each agent learning individually and executing independently of each other in a decentralized manner. So this is over optimistic, clearly, because we're sort of hoping that agents can learn anyway, and this can work sometimes. So there are notable papers that show that independent learners work sometimes better than joint learners in certain scenarios, but overall, this is not true. There are also papers that prove that this, and this is something that you could expect, of course. So in independent learners, anyway, the stochasticity is even higher compared to joint learners. In joint learning, instead, the agents use all the available information and train, execute as if they were a single agent in a centralized manner. So they can also share the observation sometime by means of communication and stuff like that. So this is why I was mentioning also the state, the observation that the agent sees, the function depends on, generates a different categorization of the approaches. So while the problem of independent learners is the stochasticity and all the issues that we have discussed before are completely ignored, so making the problem even more hard, joint learners have another problem, which is the scalability, because as long as you have only two agents, it's mostly fine. But basically the input, so the observation and the action sides, because they all execute together, compound very easily. So it's exponential, grows exponentially in the number of the agents. So this is a problem. Okay. So there is this survey that actually, before I move on to that, are there questions? Is it clear what is the basically the taxonomy of the multi-agent reinforcement learning setting? Do you have questions? If so, interrupt me. Okay, apparently not. Okay, so as I mentioned, I have found this survey, the survey and critique of multi-agent deep reinforcement learning to be very interesting. And I decided to base my presentation on top of this paper. So they categorize the multi-agent deep reinforcement learning algorithms, the most recent ones, in 4 categories, which are different from the ones that we discussed based on their application. So these 4 categories are analysis of emergent behaviors, learning communication, learning cooperation, and agents modeling agents. So we'll be focusing our presentation mostly on learning cooperation, because this includes also the mixed setting. We'll briefly talk about emergent behaviors and agent modeling agents, and learning communication will be arising in different papers that we'll touch in these other categories. But if you remember, analysis of emergent behaviors, this is something that we have already seen, right? When I was presenting, probably at the first lecture, the paper from OpenAI where they were playing hide and seek. We already discussed the fact that this was simply arising from the interaction of the agents between themselves and in the environment. And there was, and this was a multi-agent reinforcement learning problem. And we didn't discuss the details of that, of course, but the idea is exactly what we just described. But let's focus on learning cooperation. So the papers that I think would be are the most interesting for us to go through are Fingerprints, not in this order. They are Fingerprints, VDN, value decomposition networks, comma, and multi-agent DDPG. We'll start with Fingerprints, then we will go to multi-agent DDPG, VDN, and then comma. I hope I remembered the order correctly. So let's start with fingerprints. So this is a paper whose goal is exactly that of solving one of the issues that we have described to belong naturally to the multi-agent reinforcement learning problem, which is the fact that experience replay becomes very quickly, the data that are in experience replay become very quickly useless. So Forster et al. It's the name of the authors, of course, Forster and other people. They came up with this idea of stabilizing the experience replay by means of this idea of fingerprints. We'll see what this is, but I want to say that there is also the code available in this link. And I don't think this is the original code from the authors, but it should be quite reliable. So where are we collocated in this taxonomy? So we are in the setup of independent Q-learning agents. So we are in the independent learner setup. So each agent has its own experience replay, and this needs to be fixed because, as we say, the dynamics that generates the data no longer reflects the current dynamics because the agents changed, the environment changed. And then the idea that they had is, what if we use the age of this sample data from the replay memory to give less or more weight to the update that we do using this data? And this is an idea which is similar to importance sampling, although in its implementation for fingerprints, it's different. But in fact, one of the things that they propose is exactly importance sampling, and then they come up with the idea of fingerprints, and they also compare these two approaches. So the multi-agent importance sampling, in this case, allows us not only for off-policy learning, but also for off-environment learning. So this is similar to importance sampling standard in reinforcement learning, except that now we're doing, instead of policy, off-environment. So how can we do this? We know how the environment changes because this changes as a result of the policies. And so we can account for that by storing in the experience replay, instead of only state, action, reward, and next state, also the probability distribution for the actions given the state. Okay, so this is the policy. So this is the probability distribution over the set of actions to be executed given the state that is stored in the experience replay. And then if we have this information, we can compute a ratio that depends on the pi at storage time and the policy, also the probability distribution at sampling times. And this basically tells us how much things are changing. But this is, first of all, not as easy to implement. I mean, it's quite easy, but it's not as efficient because these important ratios have high variance and they are fine for the full observability setup. But when you are when you break the assumption, things become a bit worse. So the other idea that they got was, okay, what if instead of doing this, we allow the agent itself to disambiguate between new and old data? And in order to do that, what are the typical things that you would think of? You can use the iteration of training. This is telling us how far we are in training, so how much the environment has changed. And also the epsilon of the epsilon greedy, which is used typically for exploration. And generally, when you do training with epsilon greedy policies, the epsilon has a decay so that the exploration diminishes together with the number of iterations. So if you also take into account with this, which is correlated with performance for the exploration side of things, then you could think of allowing the agent to learn by means of not only the observation itself, but also the iteration, the training iteration, and the epsilon. So what happens to the Q function? Well, it needs to be trained. We not only pass the observation, so we have Q that receives the observation, but in this case, in addition to the observation, it also receives epsilon and E, where E is the training iteration. And so if we do this, they tried a bunch of experiments, and they compared no XP, which is no experience replay, XP, which is standard experience replay, and then XP plus ES is important sampling, experience replay plus fingerprints is green, and all of them together, you will see that basically fingerprints alone outperform even in many cases important sampling plus fingerprints. They of course outperform no experience replay at all, because when with the increase of the number of episodes without experience replay, the agent forgets previous experiences, and so the performance degrades. And experience replay alone, of course, also for different tasks is not always sufficient. But again, if you use fingerprints, the agent is now capable of learning, the agents are now capable of learning in this multi-agent scenario, even in the independent learning setup. And so this is the first result that is telling us something, that basically while we have all these challenges, there are solutions that can be adopted in order to reduce the impact of them in the training. So we'll now be trying to see solutions to each of the issues that we have discussed. So we said experience replay breaks, and this is one possible solution. Another interesting work that basically reduces and goes in the direction of limiting the issues that we have discussed before is this paper of multi-agent DDPG, for which we have the original code from OpenAI, by the way. And this is a sort of simple idea, which is an extension of the deep deterministic policy gradient algorithm. And if you don't know that, deep deterministic policy gradient is nothing else than a policy gradient algorithm where the policy is deterministic, which is why it's called deterministic policy gradient. And so exploration is obtained by adding some noise during the execution for collecting data. And deep, because it's using a deep neural network, actually not necessarily deep, but a neural network. But anyway, so this is the DPG, and then this is a simple extension to this algorithm. So in this algorithm, we have, of course, the multi-agent setup where every agent has a different has an observation space and a continuous action space, an actor network which is only using local observations. Okay, so the observation for the policy is local. Then there is a target actor network, which is basically used for stability in training, but it's identical to the original actor network. So it's still using only local observations. But then, differently from how it would be in the independent learning setup, the agents have a critic network which has a joint state and action pairs. So it receives joint actions and joint states. So all the states that are visible to the agents are visible to the Q function of each agent, and similarly, all the actions that are selected by each agent are visible to the Q function. Okay, and also one important thing is that these Q networks of each agent can be shared or not. So this means that the bottleneck of the network can be the same, and then they have different heads that are used in order to optimize individually for each agent. Now, as you can imagine, the critic is basically used only in training, right? In execution, we only need the actor. So this means that at execution time, each agent doesn't know what others are doing, but thanks to the information collected by means of the queue function, which is instead aware of the global state, the algorithm is capable of performing much better compared to individual agents. So here, what we see is that the queue function, which is the critic, which is the thing that is optimizing the policy, is aware of everything. And then the policy, by means of the signal coming from the queue function, learns to live in this world where it doesn't know what others are doing. It only has local observations, but it's easier to distinguish between the different settings. So basically, by having this join action and state space for the queue function, we are sort of reducing the non-stationarity problem that is caused by the fact that we have agents that are executing in parallel in the environment. We reduce this problem at training time. There's no stationarity for the agent. So learning is faster, performance is better. Okay. So more practically, the experience replay for training, which is used by the queue function, stores transitions, of course, from states to next states, but also the actions of all the agents and the rewards of all the agents. Okay, so you can imagine that there is some sort of communication between the agents that allows them to share this information. And there is this centralized entity that collects all this data and then dispatches them to the different queue networks. And then each queue network is optimized by simply minimizing the mean square error between the target, which is computed in the standard queue learning way, except that it accounts for all the actions it accounts for all the actions of the agents. And yeah, it just accounts for all the actions of all the agents. And then for the policy learning side of things, each policy individually is optimized by receiving the critique from the key network, which looks at the current state, the actions of all the agents, and then returns a signal to the policy. Now there is a video, but before we do this, in this paper, they are basically comparing multi-agent DDPG with independent learners, each of which runs one of these algorithms, being specifically DDPG, reinforced, actor critic, TRPO, and DQN. And as you can see, not only the multi-agent DDPG is capable of achieving a higher performance, so the mean episode reward is higher, but also it goes up quite more quickly compared to many of these algorithms. Now let's watch this video and see what are the performances that they get. So it goes a bit fast sometimes when it describes the task that the agent is trying to solve. So if you want me to pause, let me know, or if you missed something, just let me know, I can go back to it. And there shouldn't be any audio here, so I can talk on top of that if you want. Okay, so this is the first task, cooperative communication. So this is a comparison between multi-agent DDPG and DDPG alone, which is not capable of solving the task. Similar story here. The DDPG compared to multi-agent DDPG performs much worse in this physical deception task. Now there is adversarial chasing. So there is the green agent that runs DDPG and the red one that runs multi-agent DDPG. So the red agents have to cooperate in this mixed setting, basically, because there is cooperation between the agents, but also there is a competitive setting in trying to win against this other agent. There's cooperative navigation, which is all the agents need to cover all landmarks. And this is a non-trivial task, by the way, because it often happens with these algorithms that the agents stay stuck. They all want to go to the same place and they just get stuck with that. So these algorithms, this algorithm, the multi-agent DDPG, as you see, works also for the mix setting, as you can imagine. So it's not only pure cooperative, but also this mixed setting. So it's interesting how they all cooperate in order to just chase the single one of the two DDPG agents. Okay. So let's move on. Now,
I have a question on.
Sure.
If I understand correctly, the critic sees everything, right?
Yes, the critic sees everything.
So there's like one critic for all the agents?
No, each agent has its own critic, but it sees everything. However, they can have shared weights, which means that you can imagine like if there was a single neural network here, which receives everything, and then it has multiple heads, meaning that they have different outputs for each agent that are just independent from each other. But the core, the bottleneck of the neural network could be shared.
Okay, thanks.
Okay, so moving on, we have this other paper still from Förster. I don't know if I'm pronouncing this well or not, but this is how I think it should be pronounced, and I'll do that like this. So this paper is counterfactual multi-agent policy gradients, which is also short named as comma, which is maybe an unfortunate name, at least in Italian. But by the way, there is the implementation again available here, and this is not an official implementation, but it's a valid implementation. This comma algorithm is designed for the fully centralized setting, but it doesn't suffer from the scalability and non-stationarity issues. And specifically this paper, we have seen one paper that tries to solve the breaking of the experience replay, the other paper that tries to solve the non-stationarity issue. This paper instead tries to solve the credit assignment problem. Specifically, it does that by using an advantage function. So the advantage function typically is computed in reinforcement learning, in single agent reinforcement learning, by computing the difference between the Q function for certain action and the value function. So this is telling us how good is an action compared to the average action. This is the way we typically compute the advantage function. In this case, the comma algorithms attempts to account also for all the other agents. So instead of using the value function as a baseline, it uses a counterfactual baseline, which is computed by marginalizing over the actions of all the actions of the agent, and keeping all the other agents' actions fixed. So what is this telling us? This is telling us how much a certain action is impacting this in this difference, right? So what we want to do is basically compare the current Q value, right, to this marginalized counterfactual baseline. So again, this is giving us an information of the impact of each agent's action compared to all the other agents' actions, and by taking the difference between the Q value of the agent for a certain action and how much all the actions of a certain agent make an impact on the Q function. So it's basically separating out each agent's contribution to the overall Q function, and then putting out the difference for each specific action. And also here, if you, I mean, there is some comparison between different algorithms, but you can see that in different tasks, the win rate for comma compared to other algorithms is much higher. And the idea is very simple for this algorithm, but still is very effective, because again, it's trying to isolate the contribution of each agent to the overall Q function, and then using that in order to compute the advantage function, which is a very simple idea, yet very effective. Finally, on this set of papers that we are seeing under the cooperative setting, the cooperation setting, we have this other paper, which I think is very interesting, which is the value decomposition networks, which has an implementation at the same link that I shared before. And again, it's not an official implementation. And this is also trying to reduce the scalability issue, and at the same time work like if we were in a joint action space, while instead we're still dealing with an individual action space. How is this obtained? It's obtained by simply decomposing the team value function in some sort of additive decompositions. And basically what happens is that the network is learning a joint action value function, which is simply represented by the sum of the individual value functions. So Each agent has its own Q function. It learns its own Q function, but there is some sort of constraint in the fact that this Q function needs to be additive in order to represent the join action value function. Then this can be used, for example, for optimization, for doing actor critic or whatever you want, right? So the idea, again, also in this case is simple, but becomes very useful because you can do something like what multi-agent DDPG does, except that now you don't need to learn the Q function altogether, but you can still compute the joint action value function and then provide the gradients for the actor critic algorithm to each agent based on that. Questions on this? Okay. Okay, so in the emergent behaviors table from this paper, I wanted to isolate one paper that I think is very interesting. So this paper, this survey paper came out, I think, before the OpenAI hide and seek paper, but still, that paper would fall in this category, as I've said before. Given that we have seen that in the video, which was quite descriptive the first time, I don't think we need to go through that. But instead, I want to discuss about this paper, which is Learn Communication with an End-to-End Differentiable Model to Train with Backpropagation, which is from Peter Abil's group, which is one of the researchers that if you are interested in reinforcement learning, you should definitely be following as much as possible, because there are generally a lot of cool ideas coming up from that team of people. Okay, so this paper was published by Peter Abil and this other researcher at OpenAI, and the idea was that of designing an environment where the language is emergent in a natural way. And they did that by allowing each agent to emit actions that not only represent motion events, but also at the same time, they have to emit some symbols. So at each step, the agent emits an action, actual action, and also a symbol, which is a symbol used for communication. The reward is a joint reward function. So the agent have to cooperate. Not every agent is aware of the goals, so the agents need to communicate. And there is no special meaning that is previously assigned to each symbol. So there is some sort of vocabulary, but it's not assigned. There is no meaning which is assigned in advance to each of these symbols. So let's look at what they got. And I mean, they didn't do anything specifically fancy from the reinforcement learning perspective, but it's very interesting from the application side of things. So each agent needs to communicate in this case, and they're communicating which goals they're going to. So of course, given that there was no meaning assigned to each symbol, they did an analysis after associating basically semantics to each symbol. So they, in this task, they need to communicate because the goal of each agent is to have the other agent doing something else. So they need to communicate. For example, the green agent needs to say to the red agent, go to the red dot. And this study on emergent behaviors is something that I find very interesting, because depending on how you set up the problem, very interesting things can arise. Like, for example, as we have seen in the OpenAI hide and seek paper, there was this bug that was exploited by the agents for doing for jumping from one side of the arena to the other side. So the red agent goal, let me pause here. The red agent goal is, okay, let me go just one step back. Okay. Green agent goal is red agent should look at red. And the message that is exchanged by the green agent is red agent. So this is the receiver, the message, red agent should look at red. So it's very interesting pattern and that arises, and it's very interesting from this side of things. So, I mean, I don't think we need to look at everything, but it's very interesting to see what happens over here. Okay. I mean, if we have, given that we will have time at the end of this, if you want to go back to this, we can do it. Okay, so here we have another category of applications, actually, that we are focusing on, which is the agents that model other agents. And here specifically, I focused on two papers. I forgot to highlight another one. So one is LOLA, which is the following one, which is used in the mixed setting. And here we have also the other one which I've been focusing on is NFSP, which is instead in the competitive setting. So specifically for games. Okay, so this is another paper from Förster, and the code is available at this link. And the idea comes from the prisoner's dilemma. I don't know if you're familiar with that, but basically we have the issue is we have two prisoners, each of which can either confess or remain silent. So if they are remaining silent, they cooperate between each other. But if they confess, they are defecting. So what happens? If they both confess, they will stay in jail for 2 years each. But if only one of them remains silent and the other one confesses, the one who confessed will go would be out of jail, but the other one will stay instead 3 years. But if both of them cooperate, so both of them remain silent, so they cooperate with each other, not with the police, they remain silent without confessing anything, they will stay in jail only 1 year. So the best solution for both of them is, as you can imagine, to remain silent in this specific scenario for both of them. But of course, individually, it could be probably a better idea to confess so that you can go outside. But you don't know what the other agent is doing. So if the other agent also confesses, then you both stay in jail for 2 years. So it's very hard. So the idea of LOLA is that of including an extra term in the computation of the policy gradient that describes how the value of one agent changes depending on the other one. And specifically, it uses a second term that depends on the value function of the other agent, under the assumption that this value function is known. It starts like this. Of course, the other thing is this value function is not known. So what you can do is estimating that from samples. So then you can obtain an estimate of this term, and then understanding how you should behave depending on the how much the changes on the value function of the other agent affect yourself. So this is solving exactly this scenario, because if the first agent, let's say agent A, sees that the value of the other agent is changing towards confessing, then it should confess too, to not stay in jail 3 years, but only 2. If they both know that, if it sees instead that the other agent is remaining silent, the best thing for itself alone would be to confess, so that it stays in jail only 0 years. So there are all these different situations that can be taken into account by looking at the value function of the other agent. And this value function can be easily estimated by looking at some samples of the behavior of the other agent. Of course, not in the specific prisoner's dilemma, but in scenarios like, for example, RoboCup, this can be something useful, because you can see the behavior of your opponents. You can get some estimates from the samples that you see, and then you can use that. So this is quite interesting. So I have 2 videos linked here that I want to show. This is the blue agent, violet agent, whatever it's this color, is the LOLA agent. The OM agent is specifically the one that is using estimation for the value function, so using samples in order to compute the value function of the opponent. And let me see if I can show you these 2 videos. So this is the LOLA agent. Okay, so this is the LOLA agent. Instead, this is the naive learner. But you can clearly see that it fails to cooperate differently from the LOLA one. So the reward goes down and down and down very real quick. Okay, so last but not least, we're going to talk about this NFSP paper, which is used for imperfect information games. And imperfect information games are very important in AI. And actually, there are many papers that have been published regarding this. Actually, there is also a very nice paper called Deep Stack for an algorithm that is called for Deep Stack regarding poker. But we're not going through that now because it's kind of, it needs too many details probably. So let's focus on this. So imperfect information games are games like poker where the players are not aware of the other players' actions. So they know who the other players are. They know what are the possible strategies and actions that they can execute, as well as what are the possible payoffs for them. But they are not aware of their actions, right? This paper is from David Silver, who's now a leading researcher at DeepMind. And yeah, it's also the person who basically created AlphaGo. So I'll let this video talk. It's not from them, but it's from, I think, some presentation somewhere, but is quite well done. So I'll let this video talk. And let me make sure that the audio is being shared as well. Chat. This is the chat. Share. Share sound. Okay.
I'm going to present the paper Deep Reinforcement Learning from Self-Play in Imperfect Information Games from 2016, which focused on two-player zero-sum poker games. First, I want to start with some previous work. Previous approaches relied highly on human expert knowledges and used heuristic of card strings to abstract the game into a tractable size. Fictitious play method is an iterative method for learning Nash equilibrium. The problem is that it only applies to normal form games, which are tabular and do not capture time and sequence. The other one, fictitious self-play, is a method that fixed the above problem by integrating time and sequence using extensive form games. The idea of neurofictitious self-play is to focus on a sample-based reinforcement learning setting, where the game states does not need to be exhaustively enumerated, and the agent may not need to have a model of the game's dynamics. The structure is quite similar to FSP. It only introduces neural network as function approximator, using reinforcement learning method to find an approximation of Beck's response and supervised learning method to update the average strategy. The authors argued that NFSP was the first end-to-end deep reinforcement learning approach that approximates Nash equilibrium of imperfect information games from self-play. It is scalable without prior domain knowledge. They showed that the method converges to a approximate Nash equilibrium in the small poker game and learned a strategy in competitive with superhuman programs in the real-world scale game from scratch without using explicit prior knowledge. The next slide shows the algorithm with fated Q-learning. All the players of the game are controlled by separate NFSP agents that learn from simultaneously playing against each other. Here we have two distinct memory buffers, one circular buffer for reinforcement learning, which stores agents' experienced transition tuples that approximates data of an MDP defined by the other's average strategy profile. And the other is reservoir for supervised learning, which stores its own behavior and approximates the agent's own average strategy. And there are also two independent networks. Network Q predicts action values using off-policy reinforcement learning from past experience. This network approximates the agent's best response strategy. And network Pi maps state into action probabilities from previous best response behavior using supervised classification. This network defines the agent's average policy. So now we have two neural networks which predict actions, Q by using past experience and Pi by pulling from a history of best responses. During play, the agent will choose its action from a mixture of those two strategies. In order to ensure stability of the algorithm and simultaneously self-playing, FSP introduced two technical innovations. One is reservoir sampling to avoid windowing artifacts due to sampling from a finite memory, and anticipatory dynamics to enable qualitative changes in the stability of learning game dynamics. The idea behind this is to introduce an anticipated correction to the action, to enable each agent to both sample its own best response behaviors and more effectively track changes to opponents' behavior. As for result, they applied the method to Leduc poker using domain-independent encoding of the information state and explorability as a measurement. This one approached a Nash equilibrium where common reinforcement learning methods diverged. In the game of Limit Texas Hold'em, the agent learned a strategy directly from raw inputs that approached the performance of the state-of-the-art superhuman method based on handcrafted abstractions. In the experiments, they compared the convergence with DQN algorithm. This figure shows DQN learned a deterministic greedy strategy, which is highly exploitable.
Okay, great.
Moreover, DQN's average behavior did not approach a Nash equilibrium either. The reason behind this is that self-play experience generated by DQN agents are highly correlated over time, and the distribution of state is quite narrow. In contrast, FSP agents use a slowly changing anticipated average policy to generate self-play experience, which result in a more stable data distribution. Another experiment is to test the relevance of various components of an FSP, such as reservoir sampling and anticipatory dynamics. This figure shows that the isolation of these techniques led to divergence as well as decremental and noisy performance.
Okay, so this is basically how self-play can be used in imperfect information games. I want to see if I can at least show you the paper from Mike Bowling Deep Stack. Okay, this is paper. Okay, so this is the paper that I was mentioning, and it's one of the best computer players at poker, which has been beating humans quite a bit on that. It's this paper. I don't know if this paper specifically, but a version of this paper was published in Nature as well. And the idea here is still that of using some sort of tree search, some sort of simulation similar to what we have seen in AlphaGo, although slightly different. It uses counterfactual reasoning and Sorry, I don't know what happened. My computer died. Anyway, so why did you lose me? Can you hear me?
Yeah, we can hear you now.
Okay, so where did you? It's fine. So I was just saying that this paper is something interesting that you should be looking at, and it's. I wanted just to give you the pointer. Okay, sorry, my network is not working anymore for some reason. So I joined from phone. I'm just saying the paper that I was mentioning before is a pointer for you for the presentations that you will do for the exam. I anyway finished the slides, so at least it was not too early that this happened. And so I think we can finish here and we can reconvene next week. And yeah, sorry for the inconvenience at the end, but anyway, it is what it is. Thank you very much for your attendance and see you next week.
Thanks.
Thank you.
Bye.